Hello, everyone. Welcome to the first talk, I guess. I feel like a keynote with all the lights and everything up right now. Anyway, my name is Elvis Hovor. I work with Accenture Labs in Washington, D.C. I'm a researcher.
I'm Mohammed El Shrakawi, and I'm also a researcher at Accenture Technology Labs in DC.
Okay, so today we'll be talking about automating a very critical component within security in every organization. Specifically, we'll be talking about automating the triage and investigation of alerts and incidents in an organization. We hope that at the end of this talk, you would recognize the need for automation in this very complex, often human-driven, security process, which is incident response, incident investigations. And, we are hoping that, after going through all of this, you would chart in your mind a path to achieving true automation in your organizations. Also, we would show you two things today. We would show you a framework that we have built for extracting threat techniques, right, that you can use in building your automated incident investigation engines. And we will show you a sample automated incident investigation engine that we built specifically for the Zeus malware. So let's start with looking at some of the current challenges within incident investigations. I believe all of us are security professionals here. We do have a good understanding of the fact that we are going to get breached at one point or the other, right? Small organization, big organization, whichever one it is. It's inevitable. It's going to happen to us. So what do? We end up getting these tools that are able to help us identify threats quicker, or be able to see when we are being breached, right? These tools are giving us a level of detail that we haven't seen before. It's giving us more detail than we've ever seen. With some good tuning, it's actually helping us detect breaches quicker. But what ends up happening is that we get a flood of alerts and incidents that end up overwhelming the L2, L3 incident responders. So I'm not going to preach the choir here. We all understand that incident investigations are time consuming and resource intensive. Often it's, very human driven. And if it's human driven, it makes it a lot more costly, right? It's a very costly process. Trying to understand if, an alert is a false positive or it's a legitimate incident. Sometimes it's even a duplicate. It takes a lot of time, and I'm sure most of you understand that here. But it's often compounded when you have to actually go obtain the data that you need to do these investigations manually. Let me put this into perspective. The chart here that you see from the Ponemon Institute talks about the mean time to identify, which I believe some of our SIMs and our security tools help us with. And then it talks about the mean time to fix and the mean time to verify. I would lump that, let's say, under forensic capabilities, right? But what our research focuses on is the mean time to know. What is the mean time to know? The mean time to know for us is, the time it takes for you to validate an incident and the time it takes for you to scope a breach, right? If you look at that from here, it takes anywhere from days to weeks and sometimes months to do it. So just think about, if this is the time that it takes for you to do one, imagine the number of incidents that we get and the number of alerts that end up spewing from our systems that you need to go through. You can just imagine the number of people and the number of human resources that you need to be able to tackle some of these things. So we know it's a problem, right? Why is it that the mean time to know takes so much time? I'm sure that's what some people might ask. Why is it taking so much time? Because every time we have to deal with an incident, there are certain questions we need to ask of our data, right? How did the person get into my system? What was the adversary able to exfiltrate from my system? How did they get in there? Who are they? What do they want? All of these questions, it seems, regular questions that you would ask someone who attacks you in your home, right? But we need to ask something like this of the data. It takes a lot of time to do this for every single investigation that you have to do, and to think about doing this multiple times and not getting the data that you want, in an automated fashion, but to to go grab the data manually all the time, it's a very intensive process. So looking at this, we do have a general understanding that, we need automation in the process. We need automation to streamline this, to make it feel better, to, get it going quicker for us to be able to be on top of the breaches that are going to be able to happen, or to understand what is going on in our organization. So we recognize the need for automation, right? Let me talk about some of the benefits of automation. And I would like to make this a little bit more personal, because as a security professional, when I go into work, I want to feel like I am using my time to do something important. I want to feel like, my work time is used for doing relevant work. And I'm sure incident investigators even feel they feel more about this than I do, because, as an incident investigator, I suppose you go in there trying to slay dragons, right? You want to get the big bad guys and stop bad guys. Is that what really happens in the life of an incident investigator? Not really, no. I see someone shaking his head, because it really isn't. 11 out of your 12 hours, if you're on a 12-hour shift, you're using to do repetitive tasks, right? Trying to pull data manually for you to be able to use that one last hour to actually, investigate. And usually it's not enough time for you to do anything meaningful. So it's like you come in to slay huge dragons, and then you end up slaying a baby dragon at the end of your day. How do you feel about that, right? Automation is going to help take away some of these repetitive and mundane tasks and make it a lot more, make the incident investigative process a lot more streamlined. It's going to help with, some of the human errors that we often associate with, incident investigations. And one thing it can do also is scale up the less experienced incident investigators. What we want, what it can do is give data, or give, a way for the less skilled to be able to do more complex investigations. And I think it's going to keep everyone happy in an organization if you are able to do, more from, a junior analyst or a junior investigator. These are just some of the, advantages that you can get from automating this complex process. But there's a question that we need to ask ourselves, right? And this is a bigger question. We want to streamline. We understand how automation can help us streamline the process and, deal with the time constraints that are associated with it. But how do we maintain the level of human introspection that's often associated with a complex process like incident investigations, right? That leads me to my next slide, which is the capability framework. What is the capability framework? The idea here is, how do we capture what the human does and place it into, or give that ability to a machine to perform the same, right? Because that's what investigations are, right? We want to capture what the human does and automate that process. We know that the human often understands how a system works, right? You understand how your computer works, you understand how it interacts with the network, you know what elements exist on your computer, how data is transferred between those elements. That's knowledge that you have in your head as an incident investigator, right? Another thing that you have in your head, again, is, the techniques that you've used over time. So, as an incident investigator, at any point in your life, you probably have done you work with certain malware. You know how the malware interacts with the computer system. You understand how that works. You have used investigative techniques to look specifically at incident investigations that you've done over time, right? So understanding that knowledge of the techniques that you've used over time and how to use those techniques in an investigation and pivot and use another set of investigative techniques when they don't work, is some knowledge that you have. And the more skilled you are, the more of that knowledge that you possess, right? And in the day of an incident investigator, they bring all of this together in terms of decision making. I understand how Windows OSs work. I understand how a malware interacts with that Windows OS, and then I make a decision on which technique to use for that type of investigation. And if that type of that technique doesn't work, how do I bring up a new technique that would work for me? And if that doesn't work also, how do I build a new technique to be able to investigate that incident that I'm looking at? This is what the human does. How do we capture this and have the machine do the same? To start, let me talk about where we started from and where we are at, to give you a general understanding of what the research really has turned into. We started looking at a way for us to build, I guess, investigative playbooks, right? A reusable, platform agnostic, worker bot, which is what we called it, or a workflow to handle investigations. But, as the research progressed, we saw the need to build a better understanding of an investigation engine. What is an investigation engine? We wanted to differentiate from the end-to-end task automation, which is often associated with, automated incident investigation, and build something more of a triage engine that is able to learn, right? Why this? Because we saw that, taking or building this or codifying a set of steps that ends up, investigating an incident for you is just a way of getting, some basic level of automation done, right? I have these steps that I often follow, and that's what I use in my investigation. It's not good enough for the dynamic change in, the threat landscape and malware that we have, because it's going to be defunct no matter what you do. If you, write a set of, methods or scripts to handle an investigation, and it's just that one type, eventually the adversaries or the attackers are learning to adapt, right? It's going to be a new way, and that will be defunct. It's not going to be useful anyway. So how do we come up with a model where these investigative techniques are updated all the time, right? And we can pull from these investigative techniques to use in our automated engines. And aside from that, how do we build into our automated engines the idea of thinking, right? How to choose the type of technique to use, and, choose a different technique if that technique doesn't work, or build new techniques to be able to handle that. So that is where we are at, and that's what we wanted to do with it. We made a few assumptions right here, and that is we should be able to query the data that we need to investigate, right? We need to find an automated way of querying this data that we need to use in investigations. So we need to be able to query our endpoints to get the data that we need, query the logs, if we have a log repo or network logs, anything that is able to give us the investigative data that we need. Often it's done manually, right? Or sometimes you have some scripts that will pull some of this information for you, but we needed to do it in a way that's more automated. So that's one of the assumptions, that a company or an organization has the ability to do some of these things in an automated fashion. Another assumption is that you have, verification resources. So to be able to get, let's say, access to VirusTotal, right, in an automated way for it to check indicators for you or things of that sort, or your own internal threat intelligence database or whatever it is, to give you some indication of if your indicators are bad or not. So let me talk a little bit once more about the building blocks of what we want to do, right? These are the fundamentals. We spoke about the idea that we need to capture what the human thinks, his understanding of how the computer system works, how malware characteristics are. And the idea here is to get a comprehensive cyber ontology that brings that together. I know, right? With the moment you mention ontology, the people that understand, oh man, it's complex, right? But what is an ontology really? It's just a formal way of representing entities and the relationships that exist between them, right? It gives us ability for us to reason over data. So if we are going to take, cyber data and find a formal way of reasoning over it, at the same time capturing the human reasoning behind some of these things and putting it into a more, into reasoning rules for us to make that process repetitive, that is going to be a game changer. Specifically in incident investigations, it's going to be our understanding between computer systems, how they interrelate, right? And and how malware affects a computer system. That's the understanding that we can be able to capture using something like an incident, a comprehensive cyber ontology. Next to that, we need to capture, once again, the knowledge that skilled incident investigators have, which is how do we conduct investigations, right? Usually if I'm looking at this type of malware, I do that, and that. These are the steps that I take. Capture that and feed that to a machine for the machine to be able to learn and understand how to use that. That is also very important. Aside from that, system interconnectivity and data sharing, we use this, to explain how do we access the data, right? We are collecting data from the cyber ontology, we're collecting data from the incident investigation corpus. How do we access this data and communicate this data in such a way that the reasoning rules that we've put together on top of these is not lost, right? So you would understand that when I go investigate something and I said that I took this tool to do it because it's going to have, or it's going to give me specific artifacts from that, then that's exactly the reason why I used it. And if you pull that data, you get that same reasoning behind it. And then the cognitive decision making, that's what makes a huge difference, in bringing all of this together, right? The machine needs to understand how to make the choices that it makes and why it's making those choices. And if those choices don't work, how do I pivot and find a better way of doing it? So, how did we use this in building our model? Right? So we started looking at the comprehensive cyber ontology and bringing that together. And we used multiple ontologies, right? We used the ICAS ontology, which is from Invencia Labs, and one of our researchers in Accenture, also called Malik Ben Salim. The idea of the ICAS ontology is that it gives you the relationship between maybe computers and your network data. What elements interrelate, how it talks to each other, what data moves around. So it's really important to understand how a computer system works. We used the malware classes ontology. It's by Morton Swimmer also. That talks about the characteristics of malware. And when you fuse these two together, it's not just an understanding of computers anymore, it's also an understanding of malware and how it affects the computer, right? So you understand how it's going to affect the computer, where it's going to leave artifacts, and which part of the computer that you can find those artifacts from. So it gives you a better understanding of, or a better knowledge of how computer systems work and how malware affects the computer system. And then we layered on top of that some of these data sharing standards that we already have, right? We understand how, to share sticks information, sidewalks information, all of these things. There are all these different CREs, DFACs, there are all these various standards that we are using already, right? And it feels like they are silos. It prevents us from searching across this data evenly and not paying attention to, the standard that we need to use in kind of like in going through these the data that underlines that. This takes it away, it extracts it away, and gives us one formal way of looking at all of this data and bringing it together also. And then the investigative techniques. We collected investigative techniques and added this. This is how an investigator went about investigating a specific set of malware, and these are some of the reasons why he did that. So when you put all of this together, right, what you get is, an investigative technique for, let's say, any type of malware that you want to do. I went through this process. And when I went through this process, I understand that it affects the computer in a very specific way. But I also understand that that malware has a set of characteristics. And usually the set of characteristics that it has affects my computer in this way. And these are some of the places where I can find the artifacts related to that. So it's giving you a bigger sense of, not just the investigative technique, but how it fits into your organization also. So that is very important. It leads you all the way to some other places that you might be able to find the artifact, even if you don't know, right? It gives you a general sense of that. So let me talk about, this comprehensive cyber ontology that we built to help pull out some of the investigative techniques that we are talking about. Like I said, the comprehensive cyber ontology is a combination of ontologies that we brought together. We built this specifically to investigate the Zeus malware, so we put Zeus investigative techniques on top of it. So the ontology that we built, we put into, we are showing that in Protege, right? An ontograph in Protege. This is a visualization tool, right, to help you see the kind of data that we have in there. You can get the same data out of the ontology by writing a Sparkle query, which is basically an RDF query language, right? But we're using this to help a little bit more with the understanding, because it's visual, right, of what we are trying to do. Let's say an analyst wanted to find information about a Z-bot, right? He goes in there and just places zbot in or looks through the tree on where zbot is. He kind of understands right there and there that it's a spyware Trojan horse. It has relationships to other, Zeus malware strains or whatever you want to call them. How a spyware affects a computer. You can dig deeper. This is like levels deeper. I'm just showing it, truncated basically so that it doesn't feel, overwhelming. But you can understand what it does to a computer, how it affects a computer, how zbot specifically behaves, and then how, maybe a Zeus malware itself, the generic one, on top of that, how it's going to be related to that. You can dig deeper into, maybe a zbot, and this pop-up here is something that I just put up to show some of the indicators that I'm pulling out of that, right? So you can see some of the indicators that have been put in there by investigators to say that, these are indicators for zbot. So you know that it has some executable files usually that comes with it sometimes. That depends on the type, the strain of zbot that you're looking at, but it has some indicators. You can see some of the registry changes that it makes, the folder changes that it makes. Specifically, let's go into, let me see, I think the ntos.exe, right? And the older strains of zbot, you can find the ntos.exe file on the system. And to look at that, you can see what it does. It creates a folder. And inside these folders, you can drop a video and audio DLL. These are all indicators. It even shows you the path to find this ntos.exe file if, if your system matches what the investigator used, something of that sort. So the idea here is just to give you an idea of upscaling, let's say, an analyst or an investigator that is not really that skilled, right? He takes this information and he understands right then and then that if I need to build a workflow for a zbot to investigate, these are some of the indicators that I want. And these are some of the indicators that I need to be able to find. And these are some of even the paths to be able to get to those indicators. So let's assume that, this is what, would help someone upskill. But this is the information, this is the actual information that we are pulling out from these ontologies. The information that we are pulling out here is, multiple investigations that have been done. I'm sure when you investigate a specific malware strain, and in this case, Zeus malware, you would investigate it a little different than I would, right? Sometimes based on the tools that you have and the type of data that you have, you investigate it slightly differently. So this captures, but what I showed you earlier on captures all of the indicators that everyone was able to pull in. But this captures how an investigator went through a process, right? I did a zbot investigation and this is what I did first. And then I did that. And then I used the indicators from there to find this. So you capture that knowledge and you pull that knowledge out into your investigative engines. So instead of having just one way of doing it, which is what we do and which is what most of the tools that exist to do investigative engines, automated investigation engines do, what it does is it gives you multiple, right? It gives you multiple ways of investigating and it gives you multiple ways of updating that technique or that process so that every time there's a new way of investigation, you can add it to that and pull it back into your investigation engine for you to be able to use. That is the first part of research, which is how do we gather the information and the techniques for investigating these things. So if you are able to gather that and you're probably going to get multiple, how do you make the decision on which technique to use? And if you make the decision on that technique, if that technique doesn't work, like I spoke about, how do you, adapt and find a better technique that you can use for doing that? Another thing that we look at, and as humans, right, if you use these investigative techniques and they don't work, another thing we look at is how do we learn? As a human, you go read something and figure out how someone else did it and be able to grab that and bring that into your knowledge again. The thing with, the computer is that, or an automated engine is, it needs to do this. There's no way, what we are proposing is not a way for, to take the human completely out of the investigative loop because we are not there yet. It's not going to happen. The idea here is how do we do a due diligence with a machine and present that to an analyst or an investigator for him to go through and see that this is what we've done at least. And if that wasn't good enough, how would you do it, right? So in that same case, if the analyst does it better or is able to solve an investigative problem that, the engine wasn't able to, How do we capture that knowledge and bring it back into our system so that our system will be able to understand and use this also? With that being said, I'm going to pass it over to Mohammed, who's going to talk a little bit more about our cognitive modeling and the decisions that we made between that and how we are using that in our investigative engine.
All right, so as we spoke about earlier, we have the ontology. This is for any incident investigation. It isn't necessarily just geared towards malware. We're just using malware as our example. As Eldis showed you in the last slide for his ontology is that we have investigative steps from every investigator. I may go ahead and investigate Zeus malware in one way. You may investigate it in a different way. So how do we pick the best path out of that? That's where cognitive thinking comes into play. We use binary tree traversal along with a custom scoring engine. Now, why binary tree traversal? It all depends on every organization. We want to be able to get every single person using this catered to them specifically. So by doing binary tree traversal, we can traverse through the paths of the actual ontology and the investigators, and then add on a custom scoring engine. Because you may have specific tools in your environment that you're used to using that someone else may not have. You also may have access to all the information on an endpoint, whereas someone else may only have bits and pieces. So to be able to get all of that together is where this kind of all ties in. So custom scoring engine, this would be like a one-time manual process where you'd have to enter in what tools you have in your environment, the confidence you have in those tools, and just like what type of scores you'd give specific indicators for being confirmed. And I'll show you examples of how that works. This is a sample for checking a malicious process. We have investigator 1 who does ABC, investigator 2 who does ADE, and final investigator does ADF. Each investigator will investigate it differently. Let's go with number 1. He's going to go ahead and check running processes. And we see that explorer.exe, it was spawning off child processes that it doesn't normally spawn off. So that kind of made it a suspicious process for us. We captured the process along with the process ID. We checked the network logs to see what that process ID was tied to. We noticed that it was connecting out to 2 remote IP addresses. That, once more, just doesn't feel right. So we passed it into VirusTotal. And once more, VirusTotal, I know not a lot of people like to use it. This is just as an example. It gave us a score of 7. So going back to this custom scoring engine, the way I would do it is that anything that gives me a score of 5 or more from VirusTotal, that's an automatic 10 in my book. So that's why we go ahead and get that total score of 10 down here, and it gives the whole path a confirmation of 10. We go down the next path. We're checking the running processes again. We're going by the same process, except this time that investigator, he goes ahead and gets the hash of the process and compares it to a malicious process list. And he sees that hash matched. So that goes ahead and gives it a 10. And once more, that's because the scoring engine that we initially put in place, those are the scores that we'd assign for these sorts of confirmations. And then he went ahead and checked up for persistence in startup processes, found it, which gave that path a total score of 15. Final one, we go ahead, similar to the second investigator, but instead of checking for persistence in startup processes, he was looking for it in registry, and he was able to confirm at least one of the registry files being located there, which gave that a score of 13. So how this would work is you'd run this quite a few times, not just once. And it would go calculate which path is giving you the best score most of the time. And don't take this as an example. These will be much more filled out and just show you how the pathing would work. So we'd go through it quite a few times. And we'd calculate which path is giving you consistently the best score. That path will become your core path from then on. Now, the other paths, we're not throwing them away because they're still very good paths. We call those alternate paths. So what happens in an investigation? It would start by going down the core path since that is our primary one. It starts going down, hitting all the points. It gets to the end of the investigation. If it doesn't meet our threshold that we have set, then it's going to go down an alternate path instead. And it keeps on going until it finishes the investigation. Now, assuming that we're constantly hitting an alternate path that's giving us better results than our main path, then that alternate path will become the new core path, and the old core path will become an alternate path afterwards. Going back to another concept that we were talking about as well, is being able to learn. We need to be able to constantly learn from what new investigations there are. Going by my previous example, assume we went down the core path, assume we went down all the alternate paths. What happens if our automated engine didn't have the investigative techniques necessary to investigate this specific malware? Maybe it's a new strain that came out. We need to be able to learn from an investigator what they do and then feed that back into the greater ontology. That's where we use critical path analysis. We're going to be taking in what an investigator does after the automated engine goes ahead and does its steps, and then we collect those steps and put that back into the ontology, and I'll show you how that works. So assuming 4 different investigators right here. Investigator number 1 was looking at this malware. He checked memory, process, and then ended his investigation. Second one, process, network, software, and ended, so on and so forth. What critical path analysis does, it takes the first step and the second step of every single stage of the investigation and collects that. So we start off with memory to process, and we put that into our database. Process to network, registry to process, memory to registry, and we put a count for every single one that we've seen. Then we go to the next level, process to end, network to software, process to network, registry end. And as you can see, process to network, now the count is 2 because we're constantly incrementing. And then finally, we go to software to end and network to end. Now, how this would work, after we collect all of that information, we want to be able to recreate a path based on all these investigative techniques from all these investigators. Because as investigators, we know that when we go down a single path, one investigator might have missed a few steps to get the full scope. Another investigator might have gotten those portions. By being able to take all this information back, recreate a path, we can then have a new path that we put into ontology, which will be able to be run into more investigations. So as we see, memory, we saw process came after memory once, and then process to network, that kind of had a good count, so there's a very good likelihood that those come after each other. Software would come after network, and then we'd end the investigation. And once we saw that registry came after memory, so we went ahead and added that as an alternate path. That would be fed back into the greater ontology, in which we can then go ahead and put it into whatever orchestration engine that we have. So to give you an example of how this would work, we're going with the example of a Zeus malware. Elvis showed you that the ontology and some of the remnants that we have. We went ahead and took all those investigative steps that we had in our ontology, and we modeled that into our orchestration engine. The orchestration engine we used was the Phantom Community Edition, since it was free. There's also MuleSoft if you prefer an open source one, or whichever one you'd use in your organization normally. So here's where we start the investigation. We'd get an alert from our SIM or our IPS, IDS, whichever you have, and it would let us know that we have a malicious file on the machine. The first step we do is we get that file. After we get the file, if we have enough information from the SIM and the file itself to know what type of malware it is, we can go ahead and spawn off the correct playbook. If not, then we can do a quick file reputation using a threat intelligence database like VirusTotal, for example, and figure out that piece of information. And so we'd go into what type of malware it is, and then eventually to Trojan and Zeus malware specifically. Here's the investigative path for Zeus malware. The way it's modeled is that there are 3 different investigators that did these investigations. The middle path is one investigator, bottom path is another investigator, top path is a third investigator. We've already run binary tree traversal on these, so we know which one's the core and which one's the alternate. We have the core is the middle, and the alternates are the bottom and the top. So going specifically into what the core path does, this investigator went ahead and collected the file modifications, file names, file paths. So he's looking for remnants that Zeus malware left behind. And as we saw from the ontology, some of the remnants was ntos.exe, we have the audio DLL, we have stuff like that that we were able to know. So what we're doing is we're using OS query to go ahead and search for us on the endpoint, get that information, and then compare it to what's known for us. Second investigator, he went ahead and got the file modifications around the time of the alert. He went ahead and got the file hash of those files, and then put it through VirusTotal, as well as checking specific indicators within the registry hives. Third investigator just took the file, dropped it into Cuckoo, detonated the file on there, and then confirmed with the reports he got with VirusTotal and Zeus Tracker, and hunted for those indicators on the endpoint. Now, at the end of every investigation, we would send an email out to the investigator telling them, here's the steps that have been taken, here's what you can do about it. So this is an example of what the email would be sent out. We have step number one, we search for file modifications. We found these two files right here and we entered the core path. We can see that ntos.exe was found, so it matched one of our indicators. We increment the score from here. We start going, and it isn't until we get to comparing known malware locations that we start to see that, okay, here are some other indicators that we have. And we're constantly indicating the score. Now, as we got to the very end of our core path, we found that it didn't meet our threshold. Or our threshold that I had set was 20. I want a score of 20. If I'm going to go through an automated engine, I want it to be sure that this is what it's doing. So it only hit a score of 6 at this point. So what do? We went down the alternate path. So alternate path 1, he went ahead and started getting the hash of some of the files that were differentiated, passed those into VirusTotal, as well as looking for the specific indicators. That gave us the score that we wanted. It sent the email to the investigator and told them, hey, we need you can take action right now. And here's what we were able to gather. Here's all the information. Here's the steps that were taken, what tools were used, fix the issue. Now, assuming we didn't actually go down, get the threshold we wanted out of that alternate route, we would have gone down the third alternate route that we had. And it would have kept on going down until we met our threshold. Assuming we even didn't get that, we still would have sent the email to the investigator just saying, hey, this could be a false positive, or you may want to take a deeper look into this, but this is what we have so far. So what's next for our research? Some of the things that we can see improving on in future iterations for this is one, adding an automated layer into between the ontology and the actual orchestration engine. So at the moment, you have to take the techniques out of the ontology and model them manually into your automated engine. What we'd like to do is have something that we can do a Sparkle query with, grab the information we want from the ontology, and then feed that into using Python into Phantom, or into Java for using MuleSoft, or whatever language it is for your specific orchestration engine. The other thing is replacing our two algorithms with Markov chain. It's a neural network probabilistic algorithm that can actually improve a lot of the steps that we've been taking. So by doing this, we can actually completely eliminate the manual process of adding custom scoring to your organization. Because with the Markov chain, the way it works, I'll be in this step of the investigation. It creates a probability matrix of what the next most probable step to take is. Once it takes that next step, it creates a brand new probability matrix for the following step, and it keeps on going. And it also enhances the critical path analysis algorithm, because with Markov, you can actually influence the decisions it makes, which will enhance its decision making for future iterations of the investigation being run. And the final thing we'd like to do is actual benchmarking. So we want to compare the speed of this automated engine to an actual investigator, and the accuracy of this investigation engine to an investigator, as well as even seeing how much level of skill up does this automation engine have when you have a lower skilled investigator. With that, I'll hand it off to Elvis to wrap it up.
Okay. So let me, I guess, bring this all together, right? We have an investigative engine that kind of helps us understand the techniques that people have used to be able to find a way to update these techniques and pull these techniques out for us to be able to build our own investigative engines, right? We also have the model to reason over which of these techniques you want to use, why you want to use them based on the type of data and the tools that you have in your organization, right? And how to improve upon those techniques, right? How we gather the information, put it back into the system, and then pull it back again into our automated engines. What this gives us is the ability to stay dynamic, right? To get, these investigative techniques that we have updated all the time and fed into our engines. But when it's fed into our engines, the engine itself makes the decision on which type of technique to use, right? So we believe that it's a step ahead of what we are doing with our investigative engines now, which is a set of very static steps to follow for every investigation, and we believe that this is doing a little bit more than that. What are some of the things that we saw or we see as blockers in improving this, right? The first thing is a comprehensive ontology, and I'll talk a little bit more about this. But, to pull our knowledge into ontologies or into a format that's able to capture our reasoning rules is a huge differentiator, right? We need to figure out how do we capture the knowledge that we have in our head into a more formalized way to make things repeatable. Ontologies we have now are very piecemeal. They deal with very specific portions of the cybersecurity realm, right? And bringing them all together would make a difference. But not just that, it's bringing more data in, right? Bringing more of our knowledge in to capture all of the security realm for us to be able to reason over all of that data. So if I had more understanding of, maybe how my SIM tool works, I know how it triggers and I know where it looks for the data and how that data is affecting my actual computer system and where it's collecting that data from. That understanding is something that you can present to someone else to be able to replicate the process the way you understand it. So it's really important that we get that going. And that doesn't exist yet, right? We still have these piecemeal things, and we need to bring it all together to get that comprehensive knowledge. The investigative corpus. And I think this is the biggest problem when speaking to a lot of incident investigators, right? You are skilled because you have that knowledge of the techniques that you want to use. That's your bread and butter. Putting that out there for everyone to be able to use the same thing, it feels like you're giving away your knowledge. But, for us to, I guess as a community, as cybersecurity professionals to move forward, that's some of the data that we need to record. The truth is that there's always going to be new types of malware that you need to investigate. There's always going to be new techniques that you need to come up with. That's where your worth is. It's not old knowledge. Knowledge should be shared. And that's one thing, the investigative corpus is really important for us to add on to, some of these things that we have and be able to make sure that, we have the data that's needed for the machine to be able to learn. Otherwise, it's useless what we're trying to do. If we don't have the data to model against for the machine to learn from and to be able to improve on, then it's going to be useless for us. And then the investigation, the modeling techniques that we use. As you can see, we're using, binary tree traversal, which is probably, straightforward, right? And we're using a modified version of a critical path analysis. We wish we could use better. And like Mohammed just spoke about, we would be way better off using something like the Markov chain. But one, we don't have the data to help us support that. We don't have the investigative techniques that help us build a model like that because the data doesn't exist. And I believe that, we see right now that the Markov might probably be a better option for us based on what we look at. But I believe there's so much more to be done, right? For us to get the human thinking behind some of the reasons why we do the investigations the way we do it, we need to model that. So that's a part of, all of this that needs a lot of improvement. And I think that's something that we need to be working on also. A lot of the work that we did is from existing work, right? The models that we used and the, ontologies that we brought together and the data that we captured is from multiple places. So I like to mention some of the ones that we use a lot more, which is the ICAS ontology. I think I spoke about that a little bit. The unified cyber ontology, which was actually built for IDSs, but expanded a little bit more to do what we were trying to do with the comprehensive cyber ontology. So it brings together like things like sticks and sidewalks and how to reason over all of that data. And then we used the insider threat ontology. We wanted to do something really cool there, which was model Zeus malware and bring it all the way back to the point where we could actually see that, maybe that was triggered by an insider threat. We weren't able to get to that point, but we added that information also to see how an insider influences a system. And if we could tie back a malware all the way back to the fact that actually a malware investigation all the way back to the fact that it started from an insider threat ontology. But those are the possibilities of what we can do if we have a comprehensive ontology to help with us. So let me wrap up a little bit and talk about, the takeaways from this, right? If we take nothing at all away from this talk, what we need to understand and what I think we need to start thinking about as a community is that we need to make cybersecurity a true science. And, it's been written, if you read research papers, it's been mentioned so many times. But how do we do this? We need to capture our knowledge and make our knowledge repeatable. That's the way science is. That's the way science has been forever, right? Science has always been about capturing the knowledge and making it a repeatable set of processes so that everyone can replicate it. It's the same thing that we need to do with cyber science. And it starts with, putting our knowledge in ways that can make it repeatable, and things like an ontology is helpful, right? You capture the knowledge that you have, and it can be about anything. It could be about, not just investigations and how you do investigations, but how you understand how a tool works and how you are usually able to infer some, or do analysis based on those tools. That's knowledge that's going to be repeatable, and that's knowledge when combined to something else can be explosive if you think about it that way. So that's one of the main things that I want you to think about. And I think we've gotten to the point where we are accepting automation, right? We need to move again from that point of end-to-end task automation or process orchestration, as we call it, to understand that for us to ever model a complex process in incident investigations or whatever it is that we are doing, we need to capture the human thinking. That is very important, right? We need to capture how the human thinks and model that in the machine. That's the only way we can actually do true automation. So that's one of the things that we need to, every time we think about, automating a system and we just do an end-to-end task process, we have to remember that that's not really true automation. What else do you build on top of that? As a human, what else do you do after that? And that's what we want to start modeling also. So that's one thing I want you guys to think about more. And then, we need to contribute our knowledge. I know it's difficult. The techniques that you have for investigating and all of that, these are things that you hold close to your chest. This is something that we need to start sharing, right? We need to start sharing it to make this process better for us, to make it more repeatable, to give opportunities for other people to investigate properly. So this is our GitHub page, basically, for this comprehensive cyber ontology that we spoke about and the investigative engine that we built specifically for the Zeus malware. We are still putting some information on there, but this is what I believe is a starting point for all of us to drop in our techniques for investigation. It can be about anything, and to build even our knowledge about tools and how they exist and all of that. Let's bring it together. Let's all try and contribute as much. You can, maybe use what we started for Zeus malware, build something else, put it up there, and then, as a community, we build a better product for all of ourselves. So with that being said, I hope this talk was, informative, and you were able to find, a way for you to start building this kind of capability in your organization. So I don't believe we have time for any questions or anything of that sort, but we'll be standing right by that door. So if you want to talk to us, more comprehensively about some of these things that we are doing and where we are at and, what our thoughts are, we'll be grateful. So thank you all very much. And I hope you had a great time.